When we're transferring energy, it is exchanged through two different ways between our system and our surroundings. So the system is our chemical reaction, and the surroundings are everything where that energy gets exchanged with. And there's the two different ways that it is exchanged is through heat, which has to do with our thermal energy, and work, which has to do with a change in volume. And so heat and work, they do not depend on just the final and initial states, which is what we call a state function. Their values actually depend on the process in which they undergo. And the signs of these two different um, quantities are very important. It depends which way the energy is flowing. So if the system is gaining heat energy, it is a positive value for Q. If the system is giving off heat energy, it is a negative value for Q. Same with work. So if we're gaining energy from work, it's positive. If we're releasing energy by doing work, it's negative. And so if our overall system gains internal energy, it's positive. And if it loses energy, it's negative. And these signs are very important to carry out our calculations so that we are getting the proper quantity. So our equation that we're going to use is our change in energy. Remember, delta means change in energy is equal to the heat plus the work that is being done. Let's look at heat first. So our heat exchange is going to be the exchange of thermal energy between the system and our surroundings. And thermal energy happens when there is a difference in temperature. And that temperature is a measure of the amount of thermal energy within the sample of matter, which is related to the kinetic energy of our molecules. Because the higher the temperature, the more motion our molecules are going to have. The lower the temperature, the less motion they're going to have. And when we're exchanging energy, it goes from matter with high temperature because those molecules are moving faster, colliding with the slower moving low temperature molecules and giving them a little bit of their energy. And this is going to happen until the high temperature molecules have exchanged the energy so that the low temperature molecules come to the same amount of energy, or therefore the same temperature. And this is what we call thermal equilibrium. But we're always flowing, the energy is always flowing from high temperature to low temperature. So in the winter, you're actually, if you leave the door open, you're not letting the cold air in. You're actually letting the hot air out. So we do have something called specific heat capacity, and this is depends on the type of material that we have. So the specific heat capacity tells us the ability of that material to absorb heat. And the units that we use for this is joules per gram degree Celsius, because it's the amount of energy required to raise 1 gram of the substance 1 degree Celsius. So on the right-hand side, you see a table. You'll notice that the metals that we have much lower specific heat capacities than things like ethanol or water. So this is why we use metal in cooking utensils, because it gains that energy very quickly to transfer it into the food that you're cooking. And the high specific heat capacity of water is actually what allows us to use it for things like in your radiator to transfer that heat, because it takes a lot of energy to raise that water's temperature. And so in the radiator, it helps to pull the heat out of the engine to keep it in a safe temperature. This is also why coastal cities tend to be more temperate or more moderate in their temperature as opposed to cities that are in the interior of the country, because it takes a lot of energy that the sun will heat up the water, and that water will hold that warmer temperature for a longer period of time. And it also takes longer to cool those waters. There is another type of heat capacity, which is called the molar heat capacity. So it's similar to specific, except for the fact that our units are going to be joules per mole degree Celsius. So we do have to use our heat capacity in our calculations of heat energy. It is also proportional to the mass, and the temperature is important as well. And so if we want to calculate the quantity of heat absorbed by the object, we are going to use the equation that mass times specific heat times the change in temperature is equal to the heat of our object. So this is Q equals M times C sub S times delta T. So remember, delta is change. Change is final minus initial. So if we're going to calculate this, we need the mass of our object, the specific heat of the material that it's made out of, and the temperature change that it undergoes in order to calculate our heat. So let's look at an example. How much heat is absorbed by a copper penny with a mass of 3.1 grams, whose temperature rises from -8 degrees Celsius to 37 degrees Celsius. So this would be like if it's sitting outside on a cold winter day and you pick it up and warm that penny up to body temperature. So we are going to use our equation, Q equal to the mass times the specific heat times the change in temperature. The mass of the penny is 3.1 grams. We can go back and look up the specific heat of copper from the table that we saw previously. And for copper, 0.385 joules per gram degree Celsius times the change in temperature. So our final temperature is 37 degrees Celsius minus our initial temperature of -8 degrees Celsius. And if we do our calculation, the heat that is absorbed by that penny, 53.7 joules. Now, if we think about this, would it make sense that we have a positive heat in this case? It does, because our penny is absorbing the heat, making the temperature rise, and so it would make sense that we have a positive heat for this particular equation. Here's a practice problem for you to try. Calculate the amount of heat released when 7.4 grams of water cools from 49 degrees Celsius to 29 degrees Celsius. You're provided the specific heat. Pause the video and try your calculation. Our heat is equal to the mass times specific heat times change in temperature. So the mass of our water is 7.4 grams. The specific heat of water is 4.18 joules per gram degree Celsius. And our temperature change is final, which is 29 degrees Celsius minus 49 degrees Celsius. In this case, we get a heat equal to negative 618 joules. If we look at our significant figures, we should only have two significant figures from our temperature. So negative 6.2 times 10 to the second joules. Now, does this make sense? Well, so our heat is being released in this case from the water because it's cooling down. Our final temperature is lower than our initial temperature, so it's giving off its heat, which means that our heat should be negative. So if you're careful in the temperatures that you always take final minus initial, it helps you with the sign for the heat.